So lesson number 5 is one of 3 lessons that deal with factoring polynomials. So the rest of the chapter is a float between factoring polynomials and then graphing polynomials. So when we look at factoring polynomials, it says consider the polynomial function f of x equals x squared minus x minus 6. The function can be expressed in factored form as f of x equals x plus 2 and x minus 3. So if we look, the graph of this function has intercepts at what 2 points?
-2 and 3.
-2 and 3. And then the function f of x equals x squared minus x minus 6, which equals x plus 2 and x minus 3, has zeros at -2 and 3. And then the equation, when I let the equation equal 0 and I solve for x, I get roots at -2 and +3. So this goes back to last year when we say that the zeros of the function, the x-intercepts of the function, and the roots of the corresponding equation are the same numbers. And that's important to remember, especially when we get into the graphing of our polynomial functions. So there's an integral theorem called the integral zero theorem. So it says the factors of the polynomial x squared plus 5x minus 24 are x plus 8 and x minus 3. What would be the zeros of this polynomial function? -8 and 3. Okay. What is the constant term of the polynomial? Okay, so the constant is -24, and the zeros are -8 and 3. What do you notice about those numbers?
When you multiply them together, you get the constant.
Yeah, so the product of the zeros equals the constant. So if I look at the polynomial function x cubed minus 2x squared minus x plus 2, if I factor that polynomial function, I get 3 factors: x minus 2, x minus 1, and x plus 1. If I state the zeros of the polynomial function, what are the zeros of this function? So -1, 1, and 2. And what do you notice about the constant term? The constant, again, is +2, and my zeros were -1, 1, and 2. I think this is wrong. So this time, when I go to multiply it out, it's not the value or the product here gives me a -2, but if I was to take the absolute value of -2, I would get my +2. So if I ignore the sign in front of the constant and I look just at absolute values, they do equal up. And that gives us an important theorem, which is on the next page. It is my integral zero theorem. So it states, the zeros of an integral polynomial function that has a leading coefficient of 1 has to be factors of the constant term. So if I have a polynomial function, x cubed minus 7x minus 6, the zeros, or the factors, the zeros of this function have to be factors of -6. So it could be a positive and -2, a positive and -1, positive -3, positive -6. They are all potential zeros. So it says list the potential zeros. We already have them listed. We'll just write them out again. So each of those zeros I can then turn into a factor. So if my 0 is 1, my factor would be x minus 1. If my 0 is negative 1, my factor would be, if my 0 is 2, my factor would be x minus 2. So I have x minus 2, x plus 2, and so on. So x minus 3, x plus 3, x minus 6, and x plus 6. So what I'm looking for is I'm looking at what the potential factors could be for this polynomial. So there's two ways that I could identify which one of these, or ones of these 8 factors, are a factor of my original polynomial. I can do that 2 ways. I can use the factor theorem that we looked at yesterday, or I can look at synthetic division. So the factor theorem says if x minus 1 is a factor, I can substitute 1 into my equation. And so when I substitute 1 in, I get 1 cubed minus 7 times 1 minus 6, which gives me negative 12. Because I don't have 0 for my remainder, it's not a factor. So then I try x plus 1 as a factor. So if x plus 1 is a factor, my 0 would be negative 1. I substitute negative 1 in, and I get 0 for an answer. So then x plus 1 is a factor. Because I have x plus 1 as a factor, I can use synthetic division now to help me break apart that polynomial function. So at this point here, what I'm getting is that x cubed minus 7x plus 6 is equal to this factor, x plus 1, times this factor down here, which would be x squared minus x minus 6. And then there is no remainder, which is why this becomes a factor, because I can multiply the two things together and get my answer.
Shouldn't it be x cubed minus 7x minus 6?
Oh, minus 6, sorry. Yes. So Nicole started off with synthetic division. Tried x minus 1 as a factor, got the same thing as Luke, got that the remainder is negative 12, so it wouldn't be a factor. Tried x plus 1 as a factor, got a remainder of 0, so proved x plus 1 was a factor. So still got to the same point. Both of these get me to the same ending point. It's just what will help you to that point. I still need to do synthetic division at this step. So whether I start off and just keep doing synthetic division from the beginning, or whether I use the remainder theorem, because it might take a little bit less space, it might be a little bit shorter, I could do that as well. And then, I can complete factoring, or I can complete the factoring of this polynomial, because I have x plus 1 and x squared minus x minus 6. I can look at this quadratic. And the question that I want to answer is, how do I factor this? So I'm looking to find two numbers that multiply to negative 6 and add to negative 1. So x minus 3 and x plus 2. And I would get x plus 1. So my polynomial p of x, when I completely factor it, would give me these 3 values. So what that means as well is if instead I had started as x minus 3 in my synthetic division, I still would have gotten a remainder of 0. Because what that would have looked like, negative 1, 0, negative 7, negative 6. X minus 3 means it would be a 3 outside. And if I did my synthetic division, I get negative 16. Wait a minute, what did I do wrong here?
Negative 1.
prime remainder of 0. And then this down here would give me x squared plus 3x plus 2. Two numbers that multiply to 2 and add to 3 become 2 and 1. So x plus 2 and x plus 1. So I'm still getting the same 3 factors in the end. So it doesn't matter which one you choose, you just have to start at some point. So if we look at class example number 2, consider the polynomial p of x equals x to the power of 4 plus 2x cubed minus 7x squared minus 8x plus 12. The potential zeros of the polynomial. So when we are considering the potential zeros of the polynomial, we're looking at this constant term. And we're trying to think of what are all the factors of 12.
1, 2, 3, 4, 6, and 12. Positive and negative.
And positive and negative for each of them. So positive and negative 1, positive and negative 2, positive and negative 3, 4, 6, and 12. So now when I go to factor this, when I go to express the polynomial in factored form, I want to use some strategies to figure out what factor I should start with. So I'm going to let you in on a little trick that you can do with your calculator to help you still do this algebraically but not take 5 years to do this. So if you were to grab your calculator, and we start off with, in our y equals, we're going to type in this factor. X to the power of 4 plus 2x to the power of 3 minus 7x squared minus 8x. There. Try that again. X to the power of 4 plus 2x to the power of 3 minus 7x squared minus 8x plus 12. Then what I'm going to do is I'm going to go to my table. So if I go second table and I look at the 1, it's a 0. So when I input 1, I get 0 for an answer. So I'm going to use that to help me fast step it. So what that means is P of 1 equals 1 to the power of 4 plus 2 times 1 to the power of 3 minus 7 times 1 squared minus 8 times 1 plus 12. And that equals 0. I get 1 plus 2 is 3, minus 7 gives me negative 4, minus 8 gives me negative 12, plus 12 equals 0. So I know that 1 can be one of my numbers. So if I use synthetic division on my 1, I get 1, 2, negative 7, negative 8, and 12. 1 times 1, add, multiply, add. So then what I get is I get this new polynomial, x to the power of 3 plus 3x squared minus 4x minus 12. And then I start again. So I've already found 1, 0, 1. And when we were looking at that screen, when x equals 2, that also worked. If it works for the original function, it's going to work for the new function. So if I calculate p of 2 now, in this function, I get 2 cubed, which is 8, minus 3 times 2 squared, which is 12, so I'm at negative 4, minus 4 times 2, which is 8, so now I'm at negative. So 8 minus 12 is negative 4, minus 8 is negative 12. Did I do that right?
Yeah.
Oh. Plus 3x, there we go. Plus 3 times 4. So then I've got 8 plus 12 is 20, minus 8, minus 12. So there's my 0. So then I do synthetic division again with that 2. And I get 1, 3, negative 4, and negative 12. So 2 times 1, add, times 2, add, times 2, add. So now I've got this x squared plus 5x plus 6. Can I factor that quadratic? What do I get when I factor the quadratic? Two and 3. So I get x plus 2 and x plus 3. So then my polynomial, my p of x, in factored form would be equal to, if I have a 0 of 1, what's the factor? X minus 1. If I have a 0 of 2, my factor is, and then I have the x plus 2 and the x plus 3. So if that's my factored form, what are the zeros of the equation? And what are the roots of the equation when it equals 0? The same thing. 1, 2, negative 2, and 3. So we're going to look at the last question. It says, consider the polynomial function x cubed minus 3x squared minus 3x plus 1. It says, find the zeros using a graphing calculator. So if I take my graphing calculator and I input the equation, so I get x to the power of 3 minus 3x squared minus 3x plus 1. And then if I do a zoom 6, so a standard window setting, and then I find the zeros. So that's second trace, which is my calculation, and I'm finding the 0, which is number 2. Then I have to be on the left side and the right side. So there's the left side of 1, 0, the right side of the 0. And then I wait, and I get negative 1. If I do the next 0, this side, the left side is above, and the right side goes below because of the way that the graph is moving. And I get 0.28. So I have negative 1, 0.28, and the other one is 0.28 or 27?
I got 27.
Yeah, I can't round properly. And what's the last one? What did you get?
3.73.
So that's finding these to the nearest tenth. But I can also find the exact values of these using synthetic division. What I'm going to do is I'm going to pick out the integral 0. I'm going to pick out the 0 that I didn't have to round. That's this one. So I'm going to use synthetic division with that 0. And I get 1, negative 3, negative 3, and 1. I get negative 4, positive 4, gives me positive 1, negative 1. So I get the equation x squared minus 4x plus 1. So if I think about trying to factor this, that means finding two numbers that multiply to 1 and add to negative 4. Can you think of two such numbers? Not whole numbers, which should make sense because my zeros are not whole numbers. They're not even a nice decimal. They're something else. So if I can't factor this through inspection, what do I use? The quadratic formula, yay! Because we love the quadratic formula. That's my x equals, I'll write it up here, positive or negative b plus or minus the square root of b squared minus 4ac all over 2a. So my plus or minus b, or sorry, it's not plus or minus b, it's negative b. There we go. So I get negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 1 over 2 times 1. So the negative of the negative 4 is a positive 4. Inside the brackets, I get 16 minus 4, which is 12. And all that is divided by 2. The radical of 12, I can write as 2 root 3. Because I can rewrite 12 as 4 times 3. I'll just put that above. Square root of 4 becomes 2. That's how I get my 2 root 3. 4, 2, and 2 can all be divided by 2. So I get 2 plus or minus root 3. And if I was to grab my calculator and go to my main screen and go 2 plus root 3, there's my 3.73. That was one of my zeros. And second entry retypes it. If I go 2 minus root 3, there's my other 0. So the other thing that this factoring does is it allows you to find the exact zeros for an equation that otherwise through the graph you wouldn't have been able to do. So your questions are 2, 3, and 5, and 9,